Hello, everybody. So what we're going to be looking at today is section 2.4, sequences. Now, in the previous lecture, we did section 3.1. So we did 3.1 first, and now we're coming back to 2.4. That's the correct order that we're doing them in. Okay, so section 2.1 already done. Okay. Um, so yeah, don't be surprised at that. And let's go ahead and get started then. So first of all, we need to know what a sequence is. So what is a sequence? So this is not the definition in the book, but this is the not definition. I guess it's a definition, but this is how I'm writing it. So this is what a sequence is. So it's just a list of numbers, and the list is often infinite, so it keeps going on forever. And the order of the list matters, or the order of the terms in the list matters. Okay, and so here's a couple example sequences here. So something you'll notice is I'm using curly braces. Your book doesn't use curly braces on sequences, but your calculus class, Math 4B, will. So I'm going to go ahead and use these. So usually you'll have curly braces around a sequence. But not always. Okay. And then you see that we're naming the sequence. This first one is called AN. That's another thing that's common to do, like a subscript in. Um, you wouldn't normally call a sequence like A. You would call the sequence AN or BN or CN or XN, but not A, B, or X. There's no reason why you couldn't, but that's just not what people do. Okay. Now, the reason we do it that way, like AN, is because once you're looking at the list of terms, which in this case, you got a 2, and then a -2, and then a 4, and then a -4, and then a 6, and then a -6. These terms in the sequence, you want to be able to refer to them individually. So the way you would refer to them individually is as follows. Like you might call the first one A1. And then you could call the second one A2, third one A3, A4, and so on. You can just number them up that way. And so that's why you would probably want to call it AN. I just realized that I wrote AN and then I put an arrow that pointed to AN like I was saying something. But the N there, right? So yeah, so that's a sequence. So basically you give it a name, you list out some numbers. We're using ... to indicate that this keeps going, following some kind of pattern, and that's a sequence. And then down here, I'm giving you a new sequence called BN. And if you look at the terms in this sequence are the same as the terms in this sequence, but they're not ordered the same way, right? Like the first one here is 2. This one is -2. -2, +2, +4, -4, -4, +4, right? So they don't match because the negatives are different. So these are the same numbers, but they're in a different order than they are up here. And so because of that, these are different sequences. Okay. And that's why I say they're not the same sequence, because the order of the terms in the sequence is different. Okay. So the order of the terms matter, not just if they're the same. So it's not a set, even though we use curly braces for sets. And when you're having a set, the sets, it doesn't matter what the order is, right? So like if I say S equals set 1, 2, 3, and then I say set T is 2, 1, 3, like that, we know that set S equals set T because they have the same element, right? Or if you use the subset definition, S is a subset of T and T is a subset of S, and therefore S is equal to T. But that does not work for sequences because it's not just what numbers are in the sequence, it's what order they are in the sequence. Okay? I think that should be clear. Now, what you're going to have to do in the book at first is they're going to give you a sequence and they're going to want you to write out terms. And so often, how that is going to be organized is they give you a formula. So they give you a formula for calculating the numbers in the sequence. So this is a formula for computing the terms in the sequence. And there's no trick to this or anything. They're giving you the formula and they want to know what the first 5 terms in of the sequence are. Well, look at what we did up here. You see how I say A1, A2, A3, A4? Well, that's how we're going to number them, right? We're going to start with number 1. Now, some books will start with number 0, like A0, A1, A2, A3. We're going to start with A1 generally, unless there's a reason not to. But yeah, we're going to start with it normally. So we're going to start with 1. So if I want to write out the first 5 terms of the sequence, then the first term in the sequence is A1. And then how am I going to calculate A1? Well, you see, I put a 1 where the in is. So if I replace that in with a 1, then I should replace that in with a 1. So I should replace that in with a 1. So just all the ins are 1s. So how do I calculate A1? It's 1 over 1 squared, according to the formula, right? And what is 1 over 1 squared? 1. So that's it. So you just do that 4 more times. So A2 is going to be 1 over, according to the formula, 2 squared. So it's a 4th. A3 is 1 over 3 squared. So 1 over 9. A4 is 1 over 4 squared, which is 1 over 16. And A5 is 1 over 5 squared, which is 1 over 25. So I calculated the first 5 terms of this sequence. So if I wanted to write it out, there's various ways I could. I don't have to. Like I did what I was supposed to do, right? It says write out the first 5 terms. And, we did just write out the first 5 terms. So we did the problem, but you could also write it out this way. Like sequence AN is equal to curly braces 1, 1/4, 1/9, 1/16, 1/25. And it keeps going, so you can put a ... on the end. Like that. And then if you look in your book, where your book does not use curly braces, then, well, your book would not use curly braces. So yeah, so that's how you would do that. It's not hard. You're just going to use the formula. Okay. Then what we got is a definition of the convergence of a sequence, which this is the definition from calculus textbook, not from your textbook. But I'm not even really going to go over it the way they have it here very much. So the idea behind the limit of a sequence is if the numbers are going towards something. So like, look at this picture right here, right? I'm going to draw on it. So we've got like, there's A1. And so what we're doing is we've got ins are down here, and these are the values of AN up here. Okay, so the y-axis is the value of the numbers in the sequence. So A1 is right here, A2 is right here, A3, A4, A5, A6, A7, A8, A9, A10. And if you keep going out here, like you don't know what the sequence is going to do. Like I don't know where it's supposed to be going, but what I do know is that what they intend is for it to be leveling out there at L. Okay. And so when a sequence like levels out at a particular number on the y-axis, then that is the limit of the sequence. So when a sequence levels out at a particular value, that's the limit. Okay? And it's not going to be ever exactly equal to whatever the limit is, but it's going to approach the limit. So like as an example, if you had an equals 1 over n, then you know what that sequence looks like, right? An is 1, curly braces, 1/2, 1/3, 1/4, 1/5, dot, dot, dot. And if you go and you put these on a graph, put 1 up here. If I go 1, 2, 3, 4, 5, 6, 7, then what you get when you plot these is A1 is 1, so it's there. A2 is a half, so it's there. A3 is a third, so it's about there. A fourth is a 4, or A4 is a fourth, so it's about there. And a fifth, then a sixth, then a seventh, then an eighth, then a ninth, and so on. So what's happening there, which you should be able to identify, is that the sequence is approaching 0, right? So we got 1 to a half, to a third, to a fourth, to a fifth, to a sixth. Can't even read that. To a seventh. I should just change the thickness, shouldn't I, of the thing, so we could actually read it a little better, right? It just goes down and down and gets closer and closer to 0, right? If you kept going, on this picture, think about keep going. So like if I go like a dot, 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 and then suppose it continues on, right? What if we get down here to where like this is a 1, 2, 3, 4, 5, 6, 7, 8, 9, dot, dot, dot. You keep going, eventually you're going to get to like, 1,000, 1,001, 1,002. What are those values going to look like? Well, they're going to be so close to 0 that you can't even tell that they're not 0, right? And so the further you head out, the closer to 0 that the terms in the sequence get. And so that would be showing that the limit is 0. So the limit of an equals 1 over n is 0. Okay? And so what the definition is that they give you up here is just a formal definition of it. So what this is saying is there's a number called capital N, and if little n is bigger than big N, so they're saying if you go out far enough to the right, okay? So this part right here is saying if you go far enough, I misspelled far. So if you go far enough out to the right, that's what that says, then this happens. And so what this happens is AN is close to, I'll say very close to the limit L. That's what that's saying. And they're trying to show you that in the picture. So what they're saying here is capital N is this cutoff point right here, where on this side, all of the terms are close to L. At that point. And they're trying to show you that by this interval here. So if you're in here, you're close to L. And where does that happen? Starting at N. You go past N, then you're close to L. And what their claim is that you can do that for, like, no matter how small this interval gets, like if I draw it shorter, then that just means you recalculate a new N, but everything else is the same. And so that's just their way of saying that as you go out, the terms have to approach whatever the limit is. So in this case, the limit is 0. All right. And you did limits of functions in Math 4a. Okay. And so if you did limits of functions in Math 4a, you can actually apply everything you know about limits of functions in Math 4a to the limits of sequences in this class. So this is just kind of a note here. Note. Like the limit, let's say, as n goes to infinity of, I'll just make one up. Let's just say n over n plus 1, like that kind of limit. So this would be a sequence with formula n over n plus 1. That's just the same as the limit as x goes to infinity of x over x plus 1 in a calculus class. So you're allowed to use everything you know about limits for these limits. So nothing is really different than your calculus class. Okay, so this is really a topic that you actually do know something about. It's just that we're dealing with, sorry, I'm trying to enlarge this and it's not working. Come on. Okay. It's just that we've got these individual points on the graph now because it's a sequence instead of having a curve, right? Like if I drew a curve like this and I said, well, what's the limit as you head out towards infinity? You'd say, oh, well, that's 0. Well, we're doing the same thing, but without the curve, where it's just the individual dots on the graph. Okay, so that is the idea of the limit of a sequence. Now you're supposed to be able to find a limit if you know, you're supposed to be able to find a limit. So let's try to find one. You can't always use what you know about calculus. So I say, you know, you can use what you know about calculus, but not every one of these is the same as every calculus problem. I would recommend that the way you do this is kind of like this. So like if I want to know if this sequence converges, right, I'm not going to apply any complicated math. What I'm going to do is I'm just going to start calculating some of these. Okay, so what's A1? A1 is 3 minus negative 1 to the 1 over 2 times 1. I'm going to need a calculator for this. Give me 1 second. Right. have a calculator. So what are we doing? 3 minus, so -1 to the 1 is -1. -1, but then you have a minus. So a minus and negative is a positive. So this is actually 3 plus 1/2. So 3.5. A2 is 3 minus -1 to the 2 over 2 times 2. Well, that's going to be 3 minus 1/4. So that's like 2.75. I'm not actually using the calculator that I got. A3. A3 is 3 minus -1 to the 3 over 2 times 3. Now I'm going to need it because that's going to be 3 minus, actually 3 plus 1/6, which is, need a calculator, 3 plus 1 over 6. About 3.167. So A4 is going to be 3 minus -1 to the 4th over 2 times 4. So that's going to be 3 minus 1/8. Which is 2.875, and so on. Now, what's going to happen if you are careful about graphing these is this. You don't actually need to graph it. But if you have 3 right here, and you go 1, 2, 3, 4, 5. If you go and you put these on your graph, then you've got your first A1 is at 3.5. So let me go. So 3.5 would be halfway in here. So about like that. And then you've got 2.75 is your next one. So 2.75 would be 3/4 of the way there. And then 3.16 is going to be above 3. And then below 3. Then above 3. And so what happens on this graph is that the numbers go from above. Oh, that's big. Come on. So the numbers go from above 3 to below 3 to above 3 to below 3 to above 3. But as we go, this is 1/2 away from 3. This is 1/4 away from 3. This is 1/6 away from 3. This is 1/8 away from 3, right? So what's happening is as we go, these numbers are getting closer and closer to 3. And the more of them you calculate, the more you're going to see that. So as we go, the numbers, they get closer to 3. So 3 is the limit. Okay, and another way to think about this is this sequence here, 3 minus -1 to the n over 2n. This right here, when n goes to infinity, this is going to 0, right? Like the fact that there's an n down there means that it's pretty much like this example, right? When we had an n in the denominator, right, these headed towards 0. Well, here the top is +1 or -1. The bottom is n. N's going to infinity. So overall, this thing is going to 0. Right? So this goes to 0. Well, that goes to 0, but what's the 3 doing? Still 3. So it's 3 minus something that goes to 0. So it's no surprise that the limit is 3. because the thing that we're adding or subtracting is going away. Does that make sense? So that sequence has a limit of 3. Now, not every sequence has a limit though. So down here, we've got limit of the sequence Bn, where Bn is 2 to the n. Does it converge? What's its limit? Well, write them out, right? So B1 is 2 to the 1. That's 2. B2 is 2 to the 2. That's 4. B3 is 2 to the 3. That's 8. B4 is 2 to the 4. That is 16. And so on. So does that have a limit? No, not as a number. You want a limit as a real number, it doesn't have a limit. But you could also say it goes to infinity, right? So Bn goes to infinity. So normally we would say that that does not have a limit. Right? Does not converge. All right. But you will hear people say that the limit is infinity when it goes to infinity. And so here's the definition of that. Again, it just says if it keeps getting bigger and bigger and bigger, then it can go to infinity or diverges to infinity. And here's some helpful pictures, right? If it goes up forever, that's infinity. If it goes down forever like that, that's a limit of negative infinity, negative numbers. Not a lot to say about that. I mean, the pictures say what's happening, and this example illustrates it. Okay. Now, we have rules for limit, which I believe these rules are not even really presented in your textbook, but they're in a calculus textbook, so I went and I threw them in here as well. But the idea is if you have different sequences that have limit, then you can combine them. So like, for example, if I did the limit as n goes to infinity of the sequence just 5, that's 5. I don't know why I put curly braces around it. Limit of 5 is 5. And the limit as n goes to infinity of 1 over n, we already saw was 0, right? What else can we say? Well, that's fine. So if you know this, then what could you say? Well, if you do like the limit as n goes to infinity of, let's say, 5 plus 1 over n, you don't have to do anything super complicated there. You should just say, oh, well, what's happening? Well, the limit as n goes to infinity of 5 is 5, and the limit as n goes to infinity of 1 over n is 0. So the result is 5. Okay, but when you're applying that logic, what you're applying is this rule right here, where they're just basically saying you assume that A has a limit, and if you assume that B has a limit, then if you add them, right, if you add them here, then you just add the limits. If you subtract them, then you subtract the limits. If you multiply one of them by a constant, then you multiply the limit by a constant. If you multiply the two functions, then you multiply the two limits. So it's just showing you that you can do those basic operations even involving limits. So like on this one right here, where we say find the limit of this sequence, which looks pretty complicated, what you're supposed to do is you're supposed to say, well, I want the limit as n goes to infinity of 2 plus 5 over n plus sine n over n. Well, that's just going to be individually the limit of 2, the limit of 5 over n, and the limit of sine n over n. And so individually you can do those limits. So what's the limit of 2? 2. What's the limit of 5 over n? Well, 5 over n works just like 1 over n. So that's 0. And then the last one here, sine n over n, that limit is also 0. And we will talk about that in a second. Okay, so what's the overall limit here of 2 plus 5 over n plus sine n over n? Well, it's 2 plus 0 plus 0. So the result is 0. Okay, now what I do want to talk about is that last limit that I highlighted. We're going to figure out why that is the case. So there's a typo here in the notes, first of all. I say we used it above, but showed that this limit is 1. Well, no, 0. Okay, and there you go. And so the idea is that this uses a theorem called the sandwich theorem for sequences. And so the idea, which, let me see if I can write it. Do I have room to write it? I guess I'll write it down here. So the idea is pretty simple. So let's say you have 3 different sequences. So what do they call them here? A, B, C, A, B, C. Okay, good. So if you suppose, you know, AN is small sequence, BN is a medium-sized sequence, and CN is a big sequence. Okay? And so what that means is that the BNs are always in between the A and the C. So if you go on the picture, then if this is 1, for example, then you've got, let's say A1, oh no, that's wrong. A is the small one. So let's say A1 is the small one, so it's down here, right? And then let's say we have CN, and CN's the big one, so it must be above it. So that's where C1 is. And then since B is in the middle, it's got to be somewhere in the middle. It doesn't have to be exactly halfway, but it has to be somewhere in the middle, right? Now, if you add to this, not just this, but you also say that the limit of the small one is L, and the limit of the big one is L, then what that means is wherever L is, I'll draw L down here, that the big one and the small one both have to go to L. So if I go put L right there, and I go 2, 3, 4, 5, then the A's have to go to L because I said that that's the limit, right? So the A's go to L. And the big sequence, C, it also goes to L. So it doesn't have to go straight to L, so maybe straight to L. So maybe it goes up and then it comes down. But eventually it has to go to L. Like that. Maybe I'll even kind of just connect the dots here. Get easier to see. Well, where are the B's? Well, the B's are in between. So the B's have to stay between the red dot and the purple dots. So if I draw the B's in, there's not a lot of place they could be once you get out here, right? So the B's are stuck between the other two. So the B's are always between the AN and the CN. And so hopefully you can see what happens is if the purple curve, well, not curve, if the purple dots are going to L, and the red dots are going to L, and the blue dots have to be between them. Well, if you're between two things that are going to L, you must also go to L. So the punchline here is that if you've got this, then the limit of the Bn must also be L, because it's stuck between two things that are going to L. So it has to also go to L. And that is what this theorem says. And you'll see that the picture here is just exactly the picture that I drew anyway. All right. Now, how does that apply to this limit? Find n over n. Well, what you know about sine is that sine n, the biggest it could be is 1, and the smallest it could be is -1, right? But then if you divide everything by n, and what you get is this. So you've got 1 over n on top. So like if you draw this sequence out, you've got sequence an equals, well, I guess in our syntax over here, this would be the cn. Cn is 1 over n. And then down on the bottom, you've got the same sequence, but negative. -1 over n on the bottom, right? So you've got the -1 over n on the bottom, you've got +1 over n on the top, and then this sequence must be in between them. And, you know, I don't know exactly where those numbers are, so I'm not going to draw them in the right place. But if you do sine n over n, then what you're going to get is you get some number, and then you get, you know, some number, and it's a sine, so that means sometimes it's below 0 and sometimes it's above 0. But eventually what happens is it's stuck between those other two curves. Sine n over n is in the middle. So the sandwich theorem applies to this example. All right. And you're not going to be doing a lot with it or anything, but you know, this is just kind of an introduction to how sequences work. And yeah, so what we're going to do is we're going to define recursively defined sequences now, and depending on how much time I have, then we'll either do more or not more, depending. So let's see how this goes. All right, so we've already talked about, you know, series where I give you a formula, right? Like, you know, here's a series with a formula. I don't know why it's hard to zoom right now. Well, we already saw them, right? A couple of series with formulas, and we wrote them out. Now, what this is going to be is it's going to be what we call a recursively defined sequence. That's a sequence where you have to know elements before you can calculate elements. So let me just go down to the bottom of the page here where I got some extra room here. Give you an idea of what's going on. So suppose I give you this series or sequence. Suppose, you know, sequence Cn, where Cn is what? It could be anything. Let's just say n over n squared plus 1. Like, that's my sequence, right? If I ask you to find a couple of values of the sequence, so I say find C1, C2, and I say C1000, you can do that, right? Easy. What's C1? You plug a 1 into the formula. 1 over 1 squared plus 1 to half, right? C2, that's easy. C2, 1 over 2 squared plus 1. So what's that? That's 1/5, right? C1000, that's easy. Oh, wait, this is wrong. Top should have been 2, right? 2/5. Okay, C1000, easy. 1000 over 1000 squared plus 1. So that's 1,000 over, I think, 1,000,001. If I did that right. The point is that it's easy to write down. Okay. But a recursively defined sequence is different. So this was still easy, right? So what a recursively defined sequence is a sequence where in order to calculate a sequence, you actually refer to earlier terms in the sequence. So look at this. So this is how here's an example. Sequence Bn, B1 is 3. So I tell you what B1 is, but then in order to calculate Bn, you have to use Bn minus 1. So in order to calculate Bn, you need Bn minus 1. So what's that mean? Well, what that means is this. So we're going to write out the terms of this sequence here. So this first one is Bn. So B1 equals 3 and Bn is 2 minus Bn minus 1. That's the one we're going to write first. So how do we do it? So B1 is 3. Why? Because they said so. But how do you calculate the next one? B2. Well, if you replace this with a 2, then you're also going to need to know what n minus 1 is. So what's the n? Right? Whatever this number is 1 less. So in order to calculate B2, it would be 2 minus B1. So hopefully you can see that from the formula. But then what's B1? B1 is what we already calculated. It's 3. So once you know that, you say, well, that's 2 minus 3 then, which is -1. So then you move on and you calculate B3. B3 is going to be 2 minus, well, again, whatever the number is here, this number is 1 less. Right? So that's a 2 when we're calculating B3. So what do? Well, you fill in what B2 is. So 2 minus B2, B2 is -1, the one we just calculated. So you have 2 minus -1, which is 3. So you move on to the next one, B4. How do we calculate B4? Well, according to the formula, it should be 2 minus B3, which is 2 minus 3, which is -1. B5 is 2 minus B4, which is 2 minus -1, which is 3 again. B6, 2 minus B5, which is 2 minus 3, which is -1. So what did we get here? Well, we got B1, B2, B3, B4, B5, B6. Those are the terms in the sequence. Now the point is that in order to calculate B6, you need B5, right? And so that's a problem if you want to calculate something far off in the sequence, right? Imagine I wanted down here C1000. What if I wanted B1000? If you wanted B1000, you'd be in trouble because B1000 is F2 minus B999. But what's B999? Right? I don't know. Now on this particular sequence, I could probably guess, right? Because probably you noticed that the numbers were just going 3, -1, 3, -1, 3, -1. So actually you probably could figure out what B999 was if you thought about it. So you could figure out what B1000 is, but in general, you wouldn't know. Okay. And anyway, wherever you have a sequence like this, where to calculate one of them, you need to know a different one, that is a recursively defined sequence. So recursion is when a formula refers to itself. Okay. Define a sequence so that in order to calculate terms in sequence, you need to know other terms in the sequence. That's recursively defined. All right. Let's look at the other sequence here. So the other sequence here has a name. It's called the Fibonacci sequence. Is it 2 B's, I think? No. Fibonacci sequence. Very well known. And so there's different ways to define it. And by the way, just kind of a note, your book starts with F0 equals 0, F1 equals 1. Okay. But that's not what I said here. I said F1 is 1 and F2 is 1. That's actually the same. So it's not gonna be not gonna be any different. So I'm using F1 equals 1, F2 equals 1. The same, so don't worry about it. Okay. Now let's actually go and try to calculate these. So notice that we've got 2 values here, right? F1 is 1, F2 is 1. That's how we're getting started. But then also you have the recursion formula, and the recursion formula is this. So you actually need 2 values. Fn is Fn minus 1, Fn minus 2. So let's go ahead and try to calculate some of these. So F1 is what? 1 because I say so. All right, F2 is what? It's 1 because I say so. Right? So you start off with some certain values that are given. And then after a certain point, you have to use the formula. Now the formula here is this. So it's good to see these formulas and understand them, but it's also good to remember how particular examples work out. So like for the Fibonacci sequence, what this is saying is for any given term, you add up the previous 2. So what that looks like is, for example, if you were going to calculate like F5, for example, the way you would calculate F5 is it would be F4 plus F3. And so what you really want to understand and remember is just the relationship between this number and this number and this number. Okay. Because of the n minus 1, n minus 2. So you're just counting down there, n minus 1, n minus 2. So when we're calculating terms, it goes 1, 1, and then for F3, it's F2 plus F1. That's how you do it. So how are you going to do it? Well, you're just going to add these 2 together. 1 plus 1, which is 2. And then how do you calculate F4? Well, it's going to be f3 plus f2. Well, what are those? Those are the 2 and the 1, right? So you get 3. And you just keep doing that. So the next one, you're going to add these two together, 2 and 3. F4 and F3, which is 3 plus 2, which is 5. And at some point, you just see what the pattern is. You don't have to keep writing it. You can just start in your head adding them together because the Fibonacci sequence is not that complicated, right? So like, how do you do F6? It's just these two, 8. How do you do F7? Well, F7 is going to be the 8 and the 5. So 5 plus 8 is 13. What's F8? You add up the previous two. 8 and 13 is 21. Right? So it's not hard to calculate these, but in order to calculate F8, of course, you need the previous two. And it has the same issue that this other recursive sequence has, in that if you wanted to calculate a high Fibonacci number, you would not be able to, right? What would F, I don't know, 307 be, right? F307 would be F306 plus F305, but you don't know those. So you couldn't actually get a number there, right? So if you wanted F307, you would actually have to calculate all of the ones between 8 and 307, right? So you would have to calculate all of them from, F1 up to 306 before you could calculate 307. Okay, and that is a problem with recursively defined sequences, is that generally that's what you have to do. Okay, so that's a recursively defined sequence. So there's one more thing that we need to cover, but I'm going to cover it in the next lecture, the next video here. So the last topic on this homework is, not homework, but on this lecture notes, is finding the limit of a recursively defined sequence. But we're also going to be doing this on a computer, so I'll just do this when we do it on a computer, since I am out of time for now. All right, so that's it for now. I will see you in the next video, and we will be doing more of this.